All right, welcome to another new lecture in thermodynamics. Today I wanted to remind people that we have a problem in the homework set associated with adiabatic process, the process where there is no heat exchange across the boundary. The normal book relationship, PV to the gamma equal to a constant, does not need to be used here. You can use the ideal gas law because we have an ideal gas and substitute that for TV to the gamma minus 1, or as you're seeing here, K minus 1. I would like to remind you to review your Carnot cycle basics. We're going to be looking at the hurricane as a Carnot cycle next. And take time out to really explore the Carnot plot in terms of pressure volume space, PV space. I've got a little diagram there on the right. I think that it's worth studying to know where state 1 to state 2 to state 3 to state 4 all connect together. And I think that you're going to find a lot of value in understanding how that plot works and how that plot connects with your ideas of pressure volume plots for the vapor dome, where there's phase change. Because clearly here we don't have a vapor dome in the PV space plot for Carnot, and that's because there's no phase change, and really that's because it's an ideal gas. Next, look into your diagrams of energy conversion devices. Specifically in the lecture notes, last lecture I discussed heat engines and two types of heat pumps, and I used very simple diagramming to show how heat moves through the system and how work either goes in or comes out of the system. So study those diagrams from the lecture notes. Last announcement is to read Chapter 3. I'd like you to read through Section 3.8 in Koretsky. I've assigned supplemental reading with the author Kondaputi for modern thermodynamics. You'll find that in your Canvas announcements fairly soon, if not already. So read that Chapter 3 material in Kondaputi to really help with our collective understanding of the second law of thermodynamics, which is related to today's lecture material. All right. So the Carnot cycle that we described in the last lecture, we looked at it in terms of kind of what are the ideal concepts that Sadi Carnot described for us in terms of making that internal fluid as hot as possible, the external fluid as cold as possible, and that the fluid transfer occurs largely through an adiabatic process. The interesting thing here is that inside of Earth systems, we have an example of a Carnot engine, or at least of a system that behaves remarkably similar to a Carnot engine, and that's a hurricane. Which is great stuff for us because we do tie our energy systems to both the Earth systems in the ground and the Earth systems in the atmosphere. And so here we have a diagram from Emmanuel, author who in 1991 really analyzed this problem. And you're seeing like a cross-section of a hurricane. So if you imagine a hurricane as one of those big donut-like shaped spirals, and what you're looking at here is a cross-section. Across the x-axis is the radius moving out of that spiraling vortex, and then the y-axis is z, or altitude up into the sky. So we're going to start at a point A over here that I'm circling, and you're going to start with an isothermal expansion. So what happens is there is an air mass along the ocean that for which we see an isothermal expansion of gas, in our case, right, it's going to be nitrogen, oxygen, and water vapor. And that's isothermally expanding along the Earth's surface, moving into the inner eye of the storm. When I have an isothermal process in a Carnot cycle, and let's assume that this is behaving like an ideal gas because we're at atmospheric pressures, relatively reasonably low temperatures, there is no temperature change across that expansion, and because there's no temperature change, there is no internal energy change of that gas, of that fluid. So as the gas moves in towards the center, we have an isothermal expansion. The air is expanding, and in expanding, if we have an isothermal expansion, what we have is a pressure change. And so if you look over at table 2.2 from our textbooks over on the right, you'll see that I can determine heat and work in that isothermal expansion process by a pressure change. So here we have a pressure change, basically a decrease in pressure as you move from the outside of a hurricane to the inner eye. The next step moves up. The air moves dramatically upward in an adiabatic expansion. So you have a expansion of water and clouds. As they expand, their pressure reduces, and something that's lower pressure is going to rise up. And so we have the air rising up quickly without heat transfer across the boundary. And what happens there is we do have a temperature change. As air expands, it's transferring energy across, it's not transferring energy across the boundary, so it has to remove that energy from the gas itself. And in removing energy from the gas itself, it reduces the temperature. So we have a pressure decrease, which does not affect the internal energy of the system for an ideal gas, but we do have a temperature decrease, which does decrease the internal entropy of the gas energy. Next step is another isothermal process. This time an isothermal compression step. Of course, if it's isothermal, that means that we have no temperature change, and so delta U is equal to 0. So we have an isothermal compression step. In real life, there's still a little bit of energy exchange from a hurricane, and that's through radiative losses. Basically, the hurricane itself is glowing with energy at its temperature T at the top of the hurricane. So it loses a little bit of energy, and that's why you see this little vertical drop there. And then we close the loop. We form a cycle with the adiabatic compression step. And of course, if it's adiabatic process, that means Q is equal to 0 across if we integrate across the path. And that also means that if I see compression, what I'm seeing is an increase of temperature of the system, because now the work done on the system is pouring energy into the gas, like we're pushing energy back into the gas, we're raising the temperature of the system. At the same time, we're increasing the pressure of the system. Increased air pressure drops. So heavier gas, you could think of in a way, is just going to fall back down to that point A where we started, and the cycle just keeps on going over and over again, from isothermal expansion to adiabatic expansion to isothermal compression to adiabatic compression. And we have a real-life example of the Carnot cycle. As I'm working through these notes, I just want to remind you that feel free to pause at any point to take some additional notes for yourself and to compare with the information in your reading materials. So next, let's kind of review here. We've got two big thermodynamic concepts that I want you to be aware of as we move forward today. So the first one is what's going to be the difference between a reversible process and an irreversible process. Now, in mathematical sense, a reversible process means that I can return from state 1 to state 2 back to state 1 in a reversible path. That's not as useful to you in a pragmatic sense. So when we're thinking about an irreversible process, we're going to need something more than this idea of reversibility. For the most part, I've been encouraging you to think about reversible processes as ideal processes, like best energy transfer type of processes. And irreversible is going to have new meaning right here in this lecture and as we move forward into the second law of thermodynamics. Second idea. Deep thermodynamic question idea. What's going to be the difference between an ideal gas and water vapor? So this would be water vapor not behaving as an ideal gas. So an ideal gas, again, can be a real gas, nitrogen and oxygen in the air in our room that we're breathing right now is behaving as an ideal gas. The water vapor on a hot day and let's say inside of the compressed steam of a turbine is going to behave very differently. And the reason that they behave differently is that water vapor, when it's under higher temperature and pressure, will be susceptible to molecular interactions. And those molecular interactions are going to change the energy of the system. Whereas an ideal gas, we don't need to worry about that. The only thing affecting the internal energy of an ideal gas, as we know, is going to be change in temperature. Now, what this brings us to is just a fundamental reminder that everything out there is going to be energy, which we've kind of hit upon lecture after lecture, but now we're going to find out where everything is energy and entropy. So this is basically reintroducing the idea that you have in your early reading of molar entropy, lowercase s, which would be in units of joules per mole Kelvin. Make sure you get those units right, because this is, again, a skill, is to be able to follow units as we go through the course. Joules per mole Kelvin is going to be intensive because we are dividing out by a quantity, a molar quantity. And I ask you this question, like, what else out there has these units of joules per mole Kelvin? If you recall, we described the same units for our heat capacity, for our intensive heat capacities at constant volume and at constant pressure. And you might want to really go back and look at how are those heat capacities defined, and I think you're going to see some very close relationships between how heat capacity is defined mathematically and how entropy will become defined. Other than that, though, the ideal gas constant, R, also has the same units of joules per mole Kelvin. I want to remind you here that on page 132 of your Koretsky textbook, the author really makes a mistake. It's a classic error in identifying entropy as disorder. That is not an accurate description of entropy, and it's something that we will work very hard to never use in class. There's a great educator, Frank Lambert, who developed this secondlaw.oxy.edu site to really move forward in the modern idea of entropy, because entropy itself, there I've got the extensive version of entropy in joules per Kelvin, that's a capital S. Entropy is really going to be the measure of energy dispersal. How is energy spread out in a system? Is it organized? That's actually saying, is it arranged in certain ways? But we're talking about arrangements of quantum states, arrangements of microstates, things that have very little to do with how messy your bedroom is, or a pile of sand versus a sand castle, or something like this. So just bear that in mind. Entropy is not disorder. Entropy, for us, will always be a measure of energy dispersal. Measure of energy dispersal. Now, looking back, we've spent some extensive time dealing with the first law of thermodynamics, which we've written out in differential form. du is equal to squarely dq plus squarely dw plus squarely dw prime. Integrate that form, and you really have what we've got written up here. Delta u on the left side of the equation, the state side of the equation, that's a state change, and q and w, no deltas on those, for the path functions of heat and work. Heat and work, of course, being energy crossing the boundary. The first law is just saying, hey, everything changes in energy. Energy is always transforming from one form to the next, and such as that, the change of internal energy of the universe is going to be equal to zero. And that's fairly basic accounting here, and well, unfortunately, like most accounting aspects, it's dull. It's really boring. So, yes, we use it a lot. We've used delta U is equal to Q plus W to inform how we solve problems in the isothermal process and in the adiabatic process. We've used that pretty extensively. But it really just comes down to accounting. The kind of weird nature of the first law is the first law does not have any information about directionality of a process. In fact, all the processes that you've had in class thus far have been things where people tell you that it's an expansion process or a compression process. In reality, by the first law, you cannot tell what the actual process is. And so then we bring in the exciting second law of thermodynamics. The second law of thermodynamics is great. It conveys direction. It conveys the idea of an irreversible process. An irreversible process, better known as a spontaneous process. Basically, a spontaneous process has only got one direction to go, and reversibility of that process is just not possible without something called energetic compensation. And we're going to go back to energetic compensation time and time again in the next few lectures, so bear that in mind. The second law is all about conveying the direction of processes, of irreversible processes that are spontaneous processes, and spontaneous processes don't go back the other direction unless they have energetic compensation, better known as unless they're connected up to a pump. All right, so the cool part about this, kind of like the deep thinking part about the second law, is something called time's arrow. And you're going to read about time's arrow in your supplemental reading from Kondapudi, chapter 3. But essentially, because of the second law of thermodynamics, we really only perceive time going in one direction. Time's arrow. It's like the chemistry of the way that our brains work affects our own psychological sense of time, and it's all based on the second law. It's really fantastic and amazing stuff right in there for thermodynamics. And I highly encourage you to dig into that reading by Kondapudi, because I think that the descriptive part, the qualitative part of the supplemental reading by Kondapudi will just really give you a better understanding, and it's a lot more fun to dig into while you're thinking about thermodynamics as we describe in our notes than Chapter 3 in Koretsky. Chapter 3 in Koretsky is very valuable, useful information. It's also very dry. All right? Okay, so let's go back to a diagram that I first brought to you in lectures early on in the first law, and it's these three kind of classic systems that describe directionality for irreversible processes. They're basically three classes of processes that are out there in nature that you all know about. And let's just touch base with those. So in each one of these, we have an irreversible process. Let's start first. Okay, so the first is mechanical directionality. That's the dispersion of, say, a gas under pressure, which is why you see like a gas tank where you're opening a valve and it dispels all this gas outward, disperses the gas outward until it equilibrates with atmospheric pressure on the surrounding area. Spilling of milk, that's mechanical directionality. It's only going to spill one direction. It's not going to jump back into the milk jar. Rolling downhill on Shiggletown Gap on a bike path. Did that just a year or so ago. That is very much irreversible unless you have energy to bike back on up. So those are all mechanical directionalities. Second one is going to be thermal directionality. Thermal directionality is like soup cooling, right? You don't expect soup to magically, spontaneously become warm. That makes no sense. The only way I'd get soup to warm is if I connected it to a heat pump like a microwave and warm it back up. So thermal directionality. And then the third is chemical directionality. So when I make coffee in the morning, delightful coffee, caffeinated tea, I am causing a chemical directional reaction to happen, and you're not going to have the chemicals inside of coffee or tea leaves jump back into the leaves, jump back into the beans after you've extracted them out. There's a chemical directionality to these things. Now, for each of these three, mechanical directionality, thermal directionality, and chemical directionality, we have an irreversible, a spontaneous process. Each one of these is still describing a process that by definition, the word process means going from state 1 to state 2, an initial state to a final state. The interesting thing is, we've described states in terms of their energy addresses. The initial energy address of state 1 relative to the final energy address of state 2. The interesting thing is, like as much as we have U or H, internal energy or enthalpy states for 1 and 2, we also have states for entropy. So S is associated with state 1 and state 2. So we will have S1 and S2 as we move forward. And just like energy state functions, entropy as a state function will also be path independent. And so we can define entropy in terms of an exact ordinary differential ds. So instantaneous changes of entropy will also be a part of our problem-solving process. So now you really got to go back and say, okay, so wait, what is a reversible process then, right? And remember, reversible processes were like these idealized processes. They were best case scenarios, and I said they also had this weird twist that because of they were associated with only the first law, we can't tell the direction of them directly. And so in this case, anytime I have a reversible process, another way to look at it is that example early on in your textbook where we have small infinitesimal changes in properties of state 1 and state 2, like infinitesimal changes in pressure, because we're moving an infinitesimally small weight off of my piston going from state 1 to state 2. If I have infinitesimally small changes and I have this idealized process going from state 1 to state 2, what I also have as a consequence of that is a change in entropy with respect to time, ds dt, that is equal to a symbol sigma, Greek symbol sigma, called entropy production. And the rate of entropy change with respect to time, entropy production is the word, is equal to 0 when I have a reversible process. So entropy production becomes 0 for idealized processes. Now this is like a mathematical argument for what is a reversible process. And once again, we're seeing that the word reversible becomes less and less useful to us as a normal kind of everyday word inside of thermodynamics. Reversible really means idealized. Irreversible means spontaneous. If I have a entropy production term, entropy production reflects the dissipation of energy, the spreading out of energy that is associated with irreversible processes. If I have a spontaneous process, if I open up that valve on the gas tank and allow the helium to just expel out into the surrounding atmosphere, I'm going to have a dissipation of energy, a spreading out of energy, and my sigma, my entropy production, is not going to be equal to 0. Mathematically, if I look at our kind of initial discussion of the mathematical relationship of temperature, it's the partial change in internal energy with respect to the partial change in entropy at constant volume and moles. And so if I look at this, I see entropy's right in there. And I see that entropy is a state function, but it's a state function for energy dispersion, the dissipation, the spreading out of energy. And it tells us it's an intimate term for informing us about the reversibility or irreversibility of a process, going from initial state 1 to final state 2. Converting that around, let's say looking at an ordinary differential of entropy change, mathematically I'm going to describe it as the inexact differential form of squarely dq for reversible processes divided by the temperature of the surroundings for a reversible process. If I have an irreversible process, I have ds is going to be some value greater than the infinitesimal heat exchange that I have for my irreversible processes divided by the temperature of the surroundings. That is going to be the equation form of the second law of thermodynamics. So I present the equation form of the second law of thermodynamics in the differential form, and eventually I'm going to combine these so I'll have a greater than or equal to squarely dq over t as we move forward. You're going to look on page 132, equation 3.1 for the intensive version of this same formulation. That's in Koretsky. If I look at equation 3.2 in Koretsky, you're going to see if I take the differential form and I integrate it, I go from state 1 to state 2, and I get a change in heat that I'm looking at relative to my temperature of my surroundings. The idea here is that we're looking now at thermodynamics as energy conversion devices, which is really powerful. Once I've unlocked the second law of thermodynamics, I can think about thermodynamics as energy conversion devices. And so if I use reversible versus irreversible, or idealized versus spontaneous transformations of energy and entropy, I've got a really powerful set of tools. I'm starting to get like the full set of tools that I need to understand thermodynamics through language, through skill, and through the concepts of the first and second law. So what I'm going to ask you to do is to pause it here and diagram out this little box of, I've got, looks like 3 rows, one row split into, the first and second row split into 2 columns. Please draw this out, and I'll give you a second, and then we'll move on. So you'll see that I've got delta U written across there, because basically going from state 1 to state 2, initial to final state, is going to give me my change in internal energy. And remember, the sentence-based term for internal energy is the capacity to do any work and exchange heat. Like, it's a combination of both those. And if we wrote that delta U out in mathematical form, it'd be delta U is equal to Q plus W prime. And in our case, we're just looking at delta U is Q plus W. So let's look at what I've got. Well, I'm going to draw heat over on the left, and I'm going to draw work on the right. So delta, this is mathematically, delta U is equal to Q plus W. You can see it right there. And in this case, I'm getting more work out than I am getting heat passed out of the system or exchanged with the system. It doesn't have to be a direction right now. That, by definition, is a reversible process. Okay? Let's look at how I would have to modify this reversible process to include the dissipation of energy. So right now, I'm describing a process where the entropy production, sigma, the change in entropy with respect to time, is equal to 0. If I have an irreversible process, I have to dissipate some of that work energy as heat. It's energy that doesn't go to the work process that I'm interested in. And so in doing so, there's a trade-off, and you see that now I have more Q under that curve than I did for the reversible process. This is the spontaneous process. The irreversible process is basically dumping out more Q than I would have had if I had a reversible process. And this is where you can start to see that why I keep saying the irreversible process is idealized, because I have this firm, contained boundary of Q relative to work. Okay, my final part of this is, what if I just have a piece of electric wire and I do resistive heating of my room or of a kettle of water? Well, that's a process with no work done, no mechanical work done. It is also technically, it is also a reversible process in that we have no dissipation of energy from work to heat, because there is no work being done. So it's an all friction process is another way to look at this. So anytime I'm just doing reversible process for just heat transfer, that is basically a friction process, is a good way to look at it. You're going to want to store that diagram and kind of keep it around and think about this. This is, again, another way that I'm looking at equations and turning the equations into graphical tools to help you to think about thermodynamics as an energy conversion device. Because if I have an irreversible process, I want to know, okay, what would be the best I could do anyway? I probably won't get, never actually am I going to get 100% work out of a process, but I would like to know what kind of assumptions do I need to go from a reversible to an irreversible process when I'm doing calculations. The thermodynamics for energy conversion devices, that second tool of thermodynamics. Remember, thermodynamics was being used as a code breaker, to find out about different state variables that I didn't have measured, or it can be used as understanding energy conversion devices, which is what we're talking about right now. In practice, when I have reversibility as a term to get that zero entropy production, sigma equal to zero, to get zero dissipation of energy across my system surroundings boundary. It calls for assumptions of minimal temperature gradients between the system and the surroundings, and infinitesimally slow transfer of heat. These like tiny incremental changes of heat, which is, again, is heat is energy crossing the boundary. When I have a reversible process, what it means is so that Q reversible. What that Q reversible means is that the amount of heat transfer, energy across the boundary that's not work, is minimized, and the amount of work done, again, energy crossing the boundary, but as work, is maximized. So Q is minimized, work is maximized. Right? This is an optimal scenario, best possible process. Let's look at a final example here from your textbook to kind of explore that. The idea between the ideal reversible and the non-ideal irreversible. So we're going to go through a lot of work in the next few lectures where we have irreversible solutions that then we modify up to being an irreversible process. So here's figure 3.3. I'm going to go from a state 2, a final state 2, to a state 3. That would be, if I looked at that, just look at it on a pressure temperature diagram, I'd see that from state 2 to state 3 on that diagram, forgetting any of the other information, I see I'm going horizontally, just an increase of temperature, right? Just a horizontal movement, increase of temperature. The change of entropy there is that if I were to go from state 2 to state 3, you see that I'm going from a line that, if I read that on the left, is reversible to a curve that is irreversible. So that's actually an increase of entropy that is being bundled into state 2 to state 3. This is going to be an isobaric transfer of heat into the system. Right? It's isobaric because it's horizontal line and the pressure is on the y-axis. So I have an isobaric process from state 2 to state 3. It's also a hypothetical process, right? It's not actually something that's happening. It's a hypothetical process that I'm doing. That is an isobaric transfer of heat into the system, going from temperature 2, which is lower temperature, to temperature 3, which is higher. So how do I look at that? Well, I would say delta S in this particular case is going to be my final state minus my initial state, so that's state 3 minus state 2, lowercase s because I'm talking about intensive variables, both pressure and temperature. If you look at my plot, are going to be intensive variables, right? So we're staying with intensive variables because, again, when we want to code break in thermodynamics or solve problems, we stay in the intensive variable space as much as possible. When we want to add parts together, then we'll move it up to extensive and add those parts together. So here we go, state 3 to state 2. That's going to be, delta S is going to be defined by the second law as an integral of dq reversible divided by t. But we need to turn that into something that's a useful integral because I don't see a good way to integrate that because it's not very obvious how I'd go from Q1 to Q2 when I don't even have that data. So we do a substitution. We integrate with respect to temperature. Remember that absolute temperature scale that I was talking about where there's a relationship between heat Q and temperature T? So we're going to put in our absolute temperature scale, temperature 2 to temperature 3, and we're going to integrate this relative to temperature. And we're going to use as our scaling factor in this the intensive heat capacity because this is a sensible heat change, right? There's just a temperature rise of an ideal gas. And that would mean, if I look at this horizontal line, it's at constant pressure, so I have Cp as my integrated value. And that's going to be a value greater than 0, right? If I go from T1 to T2 and I integrate that, I'm going to have a value greater than 0. Because if I integrate 1 over T, what I'm going to get is the natural log of T3 over T2. and that makes Cp, whatever the value is, just a constant that we're going to use as a multiplier of the natural log of T2 over T3. Keep in mind that your units of a natural log are always going to be basically no units. The units of a natural log is unitless, so your fundamental unit of entropy is going to be the same units as your heat capacity, which in the very beginning of the lecture, ta-da, we saw that it will be joules per mole per Kelvin. And as long as you're following your units, doing your problem solving, you're going to have no problems with this. And it should all make sense. Now, mind blown. The idea here is that, these are just skills that are naturally tying together with thermodynamics. The thermodynamics part is really that relationship of Q and entropy relative to some temperature change. In our case here, we know that Q is related to Cp because we already see in our diagram that it's a constant pressure process. The system is not at constant pressure. The process is constrained by constant pressure. Another thing to look at this is a hypothetical process. This is a dashed line. It's not the real process. In reality, I would go from state 1 to state 2, solving that for an irreversible process, which would be an entropy change of 0. Delta S would be 0 for a reversible process, and then that would be one hypothetical path. And then I would add the second hypothetical path, which would be going from state 2 to state 3, which we just set up for solution right in front of us as the integral of the 1 over T times the constant pressure or isobaric intensive heat capacity. That's going to be a positive value. So we're going to do a temperature increase and we're going to get a positive value change of entropy. Entropy is increasing right here in this process. And the units are directly tied to the same units of intensive heat capacity. Okay, so what I've got next for you is just closing remarks here. I want you to work on the Carnot cycle, case 2, inside of Koretsky. That's going to be example 3.1. While you're doing that, please go back and revisit section 2.3 of Koretsky. It's where you were already studying the Carnot cycle, and it's got important information related to the math of the internal energy change related to a Carnot cycle, right? Delta U, Q, and W. All of our polytropic processes are built into there. The big thing here is that we're now solving for delta U, for delta S, as well as for Q and for W. And if we wanted to, we could solve for delta H, the enthalpy change, in all of these problems as well. All right, I think that's it for us today. Thank you very much for your time. Have a wonderful day, everyone.